reciprocal functions, which we have talked about before, of course, but let's just recap some of it. So if I want to draw a reciprocal graph, obviously I need the original graph first of all. Things to look out for. If the original graph is 0, then when I turn it upside down, my new graph is going to be undefined. So we're probably going to have a vertical asymptote. So here's my random graph. And I've drawn my random graph, so I've tried to include every type of feature, horizontal asymptotes, vertical asymptotes, x-intercepts, and all those sorts of things. All those x-intercepts will become asymptotes. The reverse would logically be true, sort of. What I mean by sort of, if we turn those asymptotes upside down, they should theoretically become an x-intercept. However, if it didn't exist in the original function, it can't exist in the new function, so they don't actually become x-intercepts, they become point discontinuities at that x point. So that's what I mean there, x-intercepts, sort of. So, there'll be one there, and that's all. The original graph only had one, so we'll have a point discontinuity there. Now, 1's always a key feature with these graphs, so knowing where 1 is helps, because if you turn 1 upside down, obviously you get 1. So those points remain the same. And the same happens with negative 1. Turn negative 1 upside down, you get negative 1. So those points stay the same. Now, I don't know exactly what the value of this horizontal asymptote is, but if I turn it upside down, at the moment, it's looking around about a half, but it's certainly less than 1. So if I turn it upside down, it's going to become greater than 1. So I now have a higher horizontal asymptote. Okay, when the function is increasing, the reciprocal will be decreasing and vice versa. We can actually prove that with the derivative. 1 on the function x, differentiate it, you get minus the derivative on the function squared. So the derivative of the new function will always be opposite in sign to the derivative of the old function. This is why, when the original one's increasing, the new one will always be decreasing. And the sign's going to stay the same, because turning it upside down is not going to change where is it positive and where is it negative. So all right, let's just shade in the areas where the curve's going to go. So how have I worked this out? 1, of course, was the key point. Here the blue curve was totally below 1 and above the asymptote. Turn it upside down, then it'll become below the asymptote, above 1. The next section's the reverse situation, above 1. So this time it'll totally go below 1, but of course it can't all of a sudden become negative. That's where the point discontinuity is going to come in handy. That's going to allow it to go into the negative. So then to the right-hand side, it's the same idea. I mean, below 1 goes above 1 goes below 1, and so on and so on and so on. Now, there's our derivative, as I said, minus the derivative of the function squared. So that's how I know about the increasing and the decreasing. But let's also have a look at it. Minus the derivative of the function squared. So stationary points on the original graph, so the derivative is equal to 0, will also be stationary points in the new graph, because that derivative will still be 0. Okay? The y value will change, but there'll still be turning points and so on. So we've got 1 up here. Its y value was above, fair way above 1, but it's also above the horizontal asymptote, so the new one will be below it. And over here, well, again, 1, turn upside down, you get 1. So there's my graph. When I put all that information together, I know bend towards the asymptotes, all that sort of stuff, we end up with our new graph. That is what most people will miss in a question like that. They'll make it an x-intercept rather than the point discontinuity. Okay, so there's the first one.